You're staring at a storm larger than Earth itself. It has been churning for at least 190 years without stopping. Wind speeds hit 432 kilometers per hour at the edges. The center stays locked at 22 degrees south of Jupiter's equator, like it is bolted there. And scientists just figured out it is not what we thought it was. Not even close. Jupiter's Great Red Spot. The name lands like a brick, but the thing itself is stranger. An oval vortex of red-orange clouds spinning counterclockwise in a high-pressure cell, while everything around it tears past in opposite directions. For almost 2 centuries, we watched it shrink decade by decade, and nobody could tell you why. Then, in 2024, multiple research teams from NASA, the European Space Agency, universities in Spain, California, and Yale published findings that flipped the script. The storm we see today is not the one Giovanni Domenico Cassini spotted in 1665. That one died. This one appeared around 1831 and somehow refuses to quit. The mechanism keeping it alive is weirder than anyone predicted. If you value documented planetary science and atmospheric physics like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. Also, this script is researched and factual using sources from the journal Geophysical Research Letters, published June 16, 2024, by Agustin Sanchez La Vega and team at the University of the Basque Country. The journal Science, published November 19, 2021, with Juno gravity data from Scott Bolton and colleagues, the Planetary Science Journal. October 2024, with Hubble Oscillation, data from Amy Simon at NASA Goddard, and the journal Icarus September 2024 on storm feeding dynamics from Caleb Kevaney at Yale. These are deep observational archives, cross-matched with numerical simulations and spacecraft measurements, not Wikipedia summaries. Now back to the information. September 1831. Samuel Schwabe points his telescope at Jupiter and logs a clear oval structure at the southern mid-latitude. 60 recorded observations pile up between then and 1878, when continuous monitoring starts. By 1879, the spot explodes into prominence. It stretches 40,000 kilometers east to west. 3 Earths could line up inside it. The color is deep brick red. Sketches from that era show an elongated beast locked between 2 jet streams, one pulling east, one pulling west, and it sits there spinning like a top with nowhere to go. But Cassini saw something similar 2 centuries earlier, 1665. He calls it the permanent spot. He tracks it until 1713, then loses it. 118 years of silence. When the 1831 oval appears, astronomers assume it is the same storm that somehow hid or faded and came back. For over a century, that is the story. The Great Red Spot has been raging for 350 years, maybe longer. Ancient storm, permanent fixture, icon of Jupiter. Wrong. The 2024 study led by Sanchez La Vega took every historical drawing, every photograph, every digital image from 1665 to 2023 and standardized the measurements. They tracked the length-width drift rate, eccentricity, an area of both Cassini's spot and the modern one. The data does not match. Cassini's permanent spot was 2 to 3 times smaller in length than the 1879 Great Red Spot. The drift rates are different. The shape is different. The size evolution does not line up. If you extrapolate the modern spot's shrinkage backward in time, using polynomial fits, the curves do not converge with Cassini's measurements. They diverge, 2 separate storms. Cassini's permanent spot probably died sometime in the mid-18th century. The modern Great Red Spot formed around 1831 from an instability in Jupiter's zonal wind shear. Not a superstorm, not a merger of smaller vortices, a disturbance in the meridionally sheared jet streams at 22 degrees south latitude created an elongated atmospheric cell, a protovortex that grew and stabilized through Rossby wave resonance. The simulations confirm it. Superstorm scenarios produce vortices that dissipate too fast or have the wrong shape. Vortex merger scenarios create smaller structures. Only the wind shear instability model reproduces the elongated low rotation speed, high stability profile that matches observations. So the Great Red Spot is 190 years old, not 350. Still the oldest known vortex in the solar system, but younger than the myth. And it has been shrinking the entire time we have been watching it. 1879, 40,000 kilometers long. 1930, still close to 39,000. 2004, 20,000. When NASA's Juno spacecraft arrives in orbit in 2016, the spot measures about 16,000 kilometers. As of 2024, it is down to roughly 15,000. The longitudinal extent keeps contracting. The latitudinal extent stays nearly constant. It is getting rounder, losing that elongated cigar shape it once had. Scientists call it overfilling its latitude band. The jet streams to the north and south are squeezing it, and it does not fit the same way anymore. Why does it shrink? One theory says fewer small storms are feeding it. Caleb Keaveney's team at Yale ran three-dimensional simulations using the explicit planetary isentropic coordinate model. They fed the Great Red Spot a diet of smaller transient anticyclones at varying frequencies and intensities. Control simulations left the small storms out. Results were clear. When smaller storms collide with the Great Red Spot, they pass through the high-speed peripheral ring, then circle around the main oval. They tear red clouds off the edge, creating streamers, temporary chaos, but deeper down, the Great Red Spot absorbs them. It gains energy at the expense of their rotational energy. The intense vorticity of the Great Red Spot, together with its larger size and depth compared to the smaller vortices, guarantees its survival. Before 2019, the spot absorbed maybe 2 anticyclones per year. Recently, it absorbed as many as 24 per year. That is a buffet. But the simulations show the opposite is also true. Fewer small storms mean less energy input. The Great Red Spot shrinks. Keaveney's model suggests that if the supply of smaller vortices drops the spot contracts over a period of about 2.6 Earth years. Observations from the last 50 years show exactly that trend. Fewer, smaller storms in Jupiter's southern hemisphere correlate with the steady shrinkage of the Great Red Spot. It is not dying, it is starving. The flaking events that astronomers spotted in 2019 looked alarming. Chunks of red material spinning off the western edge, dissipating into space. Some predicted the spot could vanish within decades, but those flakes are superficial, creme brulee effect. A few kilometers of surface haze peeling away while the deeper structure, 200 to 300 kilometers down, stays intact. The smaller storms are not destroying the Great Red Spot, they are feeding it. Without them, it gets smaller. With them, it stays strong, maybe even grows. July 11th, 2017. Juno makes its 7th close flyby of Jupiter. The spacecraft drops to within 8,000 kilometers of the cloud tops and passes directly over the Great Red Spot. The microwave radiometer penetrates hundreds of kilometers beneath the surface. 6 frequency channels probe different depths. Each frequency paints a picture of composition and temperature at that layer. At the deepest measurement capability, the team still detects signs of the vortex. The cone-shaped swirl of air extends far below where water and ammonia condense. The storm does not stop at the cloud deck. It goes deep. But how deep? The microwave data alone cannot give a hard number, so the team uses gravity. February and July 2019. Juno flies over the Great Red Spot twice. The spacecraft has an antenna pointed at Earth. As Juno accelerates or decelerates over the storm, the Doppler shift in the radio signal changes. The Great Red Spot has higher density than the surrounding atmosphere. That creates a localized mass anomaly, a tiny gravitational bump. The bump tugs on Juno. The tug changes the spacecraft's velocity relative to Earth. Scientists measure velocity shifts as small as 0.01 millimeters per second. Precision at the edge of what instruments can detect. The gravity signature constrains the depth. 2 independent methods both converge on the same answer. The Great Red Spot extends between 300 and 500 kilometers into Jupiter's atmosphere. Most estimates center around 300 kilometers. For context, Earth's troposphere, where all our weather happens, is about 10 kilometers thick. The Great Red Spot is 30 times deeper than Earth's entire weather system. But Jupiter's jet streams, which trap the spot in place, go down to roughly 3,000 kilometers. The storm is deep, but the currents holding it there are 10 times deeper. It is a pancake, wide at the top, thick in the middle, but still shallow compared to the forces that control it. Temperature tells another story. Infrared mapping from Juno's Jovian Infrared Auroral Mapper and the James Webb Space Telescope's MIRI instrument in 2022 revealed the 3-dimensional thermal structure. The center of the Great Red Spot is cold, colder than the regions to the east and west by 1 to 1.5 Kelvin at 400 millibars of pressure, colder than the regions to the north and south by 3 to 3.5 Kelvin at the edge. Cold air in the center causes ammonia and water vapor to condense. Thick clouds form. That is why the spot looks so opaque. The condensation creates a downwelling motion. Air sinks in the center. The high-pressure cell is a zone of subsidence. But above the main vortex in the stratosphere, there are patches of warmer air, hotspots sitting high above the storm. The temperature there spikes to 1600 Kelvin, several hundred degrees hotter than the surrounding atmosphere at that altitude. Acoustic waves rising from the turbulence below break in the upper atmosphere. The wave energy converts to heat. It is like ocean waves crashing on a beach. The Great Red Spot generates so much turbulence that the sound waves, it produces heat the air 800 kilometers above the storm. That heat zone is detectable from millions of kilometers away. Wind speeds at the edge of the Great Red Spot peak at 432 kilometers per hour. Inside the vortex, the air is almost stagnant. Little inflow, little outflow. The rotation completes one full cycle about every 7 Earth days, but the spot itself drifts in longitude. It has lapped Jupiter in the System 2 coordinate frame at least 10 times since the 19th century. The drift rate changes over time. Sometimes it accelerates, sometimes it decelerates, and in 2024, Hubble caught something nobody expected. December 2023 to March 2024. Amy Simon's team at NASA Goddard used Hubble to photograph the Great Red Spot every few days for 90 days straight. 8 observations over one full oscillation cycle. They tracked size, shape, brightness, color, and vorticity. The data showed the Great Red Spot jiggling like a bowl of gelatin. The shape oscillates, it expands, then contracts. The oscillation has a 90-day period. Scientists knew the westward drift of the storm varied on a 90-day cycle, but they did not expect the size to change with it. As the storm accelerates or decelerates in longitude, it pushes against the jet streams to the north and south. The jet streams push back, the spot bulges, then it contracts. Mike Wong at UC Berkeley compared it to a sandwich, where the slices of bread are forced to bulge out when there is too much filling in the middle. The oscillation is not random, it is tied to the wind field. Right now, the Great Red Spot is overfilling its latitude band. It is too big for the space between the jets. Once it shrinks enough to fit inside that band, the winds will lock it in place. The team predicts the spot will stabilize at a smaller, less elongated shape. The shrinkage is not the end. It is a transition to equilibrium, but the oscillation complicates predictions. The storm is not a static feature, it breathes. The red color is still a mystery. Nobody knows for sure what makes it red. Hypotheses point to chemical reactions in the upper atmosphere. Ultraviolet radiation from the sun hits compounds like ammonium, hydrosulfide, and acetylene. The irradiation produces complex organic molecules called tholins. Tholins are reddish. Lab experiments support this, but the exact chemistry is unconfirmed. Another candidate is phosphine. Juno and JWST both detected phosphine gas enriched within the vortex. Phosphine can photodissociate under UV light and produce red phosphorus particles. The 1975 study by John Lewis in the journal Science suggested that the redness of the Great Red Spot might result from photochemical production of red phosphorus. The intensity of the red coloration would then depend on the strength of vertical turbulent mixing in the atmosphere. If the Great Red Spot is a region of high dynamic activity, the model provides a self-consistent explanation for why it is redder than the rest of the planet. But the color changes. Early accounts from the 19th century describe it as deep red. Modern observations show it varies between red, orange, pale salmon, and sometimes white. The spot occasionally disappears, becoming visible only through the Red Spot Hollow, which is its location in the south equatorial belt. Its visibility is coupled to the brightness of the belt. When the belt is bright white, the spot tends to be dark. When the belt is dark, the spot is usually light. Since 2014, the spot has been taking on a ruddy orange color that is slowly intensifying. The change could be due to shifts in chemical composition or the distribution of gases within and above the storm. The James Webb Space Telescope observations in July and August 2022 provided the most detailed spectroscopy of the Great Red Spot ever recorded. The MIRI medium resolution spectrometer captured thousands of individual wavelengths, which were recombined into spectra. The spectra are rich in detail: ammonia phosphine and water in the cloud-forming troposphere, methane, and a variety of hydrocarbons in the stratosphere. By modeling these spectra, Jake Harkett and Lee Fletcher at the University of Leicester determined that aerosols and phosphine gas are both enriched within the vortex. Aerosols tower up to high altitudes. The cold center forces vapors to condense, creating thick clouds. The three-dimensional temperature structure shows that as you go higher in the atmosphere, the vortex weakens. Winds at the edge slow down. The storm signature disappears by the time you reach the lower stratosphere. The tropospheric vortex is influencing the motion of air high above, but it does not extend all the way up. Hubble and JWST together tracked winds at different altitudes. Hubble measured deeper clouds, reaching wind speeds up to 150 meters per second. JWST tracked shallower clouds at higher altitudes with maximum speeds between 50 and 70 meters per second. The combination enabled direct measurements of winds in 3 dimensions: the churning cloud decks at the base, the overlying haze layer above, the entire vertical structure of the storm. The Great Red Spot is confined by jet streams: a modest eastward jet to the south, a very strong westward jet to the north. The spot sits at 22 degrees south latitude, trapped between the two. On Neptune, dark spots drift wildly in latitude because there are no strong jets to hold them in place. On Jupiter, the jets are anchors. The Great Red Spot has been held at a southern latitude for the entire duration of telescopic observations. Its latitude varies by about 1 degree. Its longitude varies constantly, including the 90-day oscillation. But north-south, it barely moves. The jets lock it there. The position is not random. 22 degrees south is where the shear between opposing jet streams creates instabilities. Rossby waves atmospheric eddies that resonate with the flow. The Great Red Spot likely formed when a disturbance in that shear zone amplified through resonance. No singular triggering event, just ongoing atmospheric dynamics that created a self-sustaining vortex. The storm is not a relic of some ancient cataclysm. It is a natural consequence of Jupiter's wind structure at that latitude. And the wind structure has been stable for at least 190 years. But Jupiter's atmosphere changes. The south equatorial belt brightens and darkens. The south tropical disturbance appears and disappears. Between 1927 and 1939, the Great Red Spot experienced a transient increase in length. It grew at a rate of plus 0.07 degrees per year, about 80 kilometers per year. The reason was the south tropical disturbance, a large enduring feature that developed at the time. The Great Red Spot engulfed clouds from the disturbance, temporary inflation. Once the disturbance faded, the spot resumed shrinking. The average shrinkage rate from 1879 to 2023 is minus 0.18 degrees per year, about 207 kilometers per year. In recent years, that rate increased to minus 0.3 degrees per year. The spot is getting rounder, the eccentricity is decreasing, the length-to-width ratio is dropping. In the late 19th century, it was a long oval. Now it is approaching circular. The area is also decreasing. Polynomial fits to the historical data show the trend clearly. The hollow, the clear region inside the red oval, is shrinking at a similar rate. Minus 0.2 degrees per year, about 230 kilometers per year. The entire structure is contracting. Will it disappear? Some astronomers believe it could dissipate within decades if the shrinking continues. Others say the apparent size reflects cloud coverage, not the underlying vortex. The flaking events in 2019 and interactions with other cyclones might just be surface phenomena. The deep vortex could remain stable even if the visible red clouds thin out. The jury is still out. But the feeding mechanism matters. The simulations show that the presence of smaller storms strengthens the Great Red Spot. If the southern hemisphere of Jupiter produces fewer transient anticyclones, the spot will continue to shrink. If storm activity increases, the spot could stabilize or even grow. The dynamics are not one-directional. The Great Red Spot is not a static dying feature. It is a dynamic system that responds to its environment. The comparison to Earth's atmosphere is striking. Long-lived high-pressure systems on Earth called heat domes or blocks occur in the westerly jet streams at mid-latitudes. They cause extreme weather events like heat waves and droughts. The longevity of these blocks is linked to interactions with smaller transient weather systems. High-pressure eddies and anticyclones can sustain and amplify the blocks. The same mechanism appears to operate on Jupiter. The Great Red Spot is essentially a massive heat dome held in place by jet streams and sustained by smaller storms. Understanding the Great Red Spot provides insight into how similar systems work on Earth. Before Juno, scientists did not know how deep Jupiter's weather systems extended. The microwave and gravity data settled it. The Great Red Spot extends 300 to 500 kilometers deep, connected to the deep atmosphere, not just the visible cloud layer. Jupiter radiates more heat than it receives from the sun. That heat drives convection that interacts with the zonal jets in the storms. The Great Red Spot sits at a latitude where the internal heat flux the jet stream structure and the Rossby wave dynamics all align. The storm's mass anomaly detected by Juno is small but measurable. The concentration of atmospheric mass within the storm creates a gravitational signature. The signature is strong enough to nudge Juno's trajectory, strong enough to stretch and squeeze the radio waves sent back to Earth. The precision required to detect that signal is staggering. Doppler shifts of 0.01 millimeters per second. Velocity changes so small they border on the limits of measurement. But the data is clean. Both the February and July 2019 overflights produced consistent results. The mass anomaly is real. The storm has its own gravity. That gravity is a function of density. The Great Red Spot has higher density than the surrounding atmosphere because of the downwelling motion. Air sinks in the center, compressing the gases below. The compression increases density. The increased density creates the mass anomaly. The mass anomaly creates the gravitational signature. The gravitational signature proves the storm is not just a surface phenomenon. It has depth, it has structure, it has weight. Jupiter spins in 9 hours 55 minutes at this latitude, more than twice as fast as Earth. That rapid rotation creates the Coriolis effect, organizing the atmosphere into zonal jets flowing east and west in alternating bands. The Great Red Spot is an anticyclone in the south equatorial belt, a downwelling zone. High pressure cell, sinking air, cold center, hurricanes on Earth last days or weeks. The Great Red Spot has lasted 190 years. The answer lies in stability. The latitude is right, the depth is right, the size is right. Once it shrinks to fit, the winds will lock it down harder. The storm will settle into equilibrium. That equilibrium is contingent on Jupiter's conditions, but those conditions have aligned for 190 years. The aerosols within the Great Red Spot are suspended at high altitudes. The cold center forces condensation, but turbulence lofts particles upward, creating a towering cloud structure. The clouds scatter sunlight. The red particles absorb certain wavelengths and reflect others, creating the distinctive color varying with altitude. The boundary between the Great Red Spot and surrounding atmosphere is sharp. The peripheral ring, where wind speeds peak, is high shear. Inside, calm, outside, chaotic. When an anticyclone enters the shear zone, it gets pulled around the periphery, tears material off, and transfers energy to the Great Red Spot. Within hours, the smaller storm is absorbed. Over decades, those small boosts add up. Feed the spot. 24 storms per year, it maintains size. Cut to 2 or 3 per year, it shrinks. The drift in longitude is real but slow, about 1.75 degrees per month westward. The drift rate varies with the oscillation, with the brightness of the south equatorial belt with transient features. And that is the strange truth. The Great Red Spot refuses to die not because it is indestructible, but because it is in balance. The jet streams trap it. The smaller storms feed it. The internal heat sustains it. The cold center organizes it. The depth anchors it. Every part of the system reinforces every other part. The storm is not fighting against Jupiter's atmosphere. It is a natural expression of Jupiter's atmosphere. It exists because the conditions are right, and the conditions have been right for 190 years. Juno's gravity measurements from July 2019 showed velocity perturbations of 0.01 millimeters per second as the spacecraft passed over the storm. That precision came from tracking the Doppler shift in the radio signal sent back to Earth over 400 million miles. The radio waves stretched and squeezed as Juno wobbled slightly in its orbit. Those wobbles translated into mass anomalies. Those mass anomalies translated into depth estimates. The chain of inference is long, but the conclusion is solid. The Great Red Spot is 300 to 500 kilometers deep. Period. The Hubble observations from December 2023 to March 2024 captured the oscillation for the first time. Amy Simon said, "We knew the motion varies slightly in longitude, but we did not expect to see the size oscillate. As far as we know, it has not been identified before. This is really the first time we have had the proper imaging cadence. The 90-day cycle was hidden in plain sight." Observers had seen the storm for 190 years, but nobody had watched it continuously over a full oscillation period. Hubble provided that continuous coverage, 8 observations over 90 days. Each observation tracked size, shape, brightness, color, vorticity. The data revealed the breathing motion. The storm is not static, it pulses. Mike Wong's sandwich analogy landed clean. The slices of bread are the jet streams. The filling is the Great Red Spot. When the filling expands, the bread bulges. When the filling contracts, the bread relaxes. The oscillation is a mechanical consequence of the storm overfilling its latitude band. Once the storm shrinks to fit, the oscillation will stop. The jets will lock the storm in place. The breathing will cease. The spot will stabilize. That is the prediction. Time will tell if it holds. The 2024 study from Sanchez-La Vega used historical sources dating from the mid-1600s and numerical models running on supercomputers at the Barcelona Supercomputing Center. 3 scenarios were tested: a superstorm, a merger of smaller vortices, an elongated cell from wind shear instability. Only the 3rd scenario reproduced the observations. The superstorm dissipated too quickly. The merger produced the wrong shape. The wind shear instability created a protovortex that grew into the Great Red Spot. The simulations used the shallow water model and the epic model. Both models converged on the same conclusion. The Great Red Spot formed from a disturbance in the meridionally sheared zonal winds at 22 degrees south latitude. No ancient origin, no mysterious trigger, just fluid dynamics. The flaking events of 2019 looked dramatic in the images, chunks of red material peeling off the western edge. But Agustin Sanchez-La Vega said this is really getting buffeted, but the flaking is superficial. The tearing of red clouds from the main oval-formed streamers, but the effect only goes down a few kilometers. The 200-kilometer depth of the storm remains intact. The flaking is like foam blowing off the top of a wave. The wave itself is fine. The Great Red Spot is not disintegrating. It is shedding surface material while the core remains stable. The temperature measurements from JWST in 2022 added detail. Jake Harkett and Lee Fletcher used the Mirai instrument to map the thermal structure in 3 dimensions. The cold center, the warm patches above, the gradients at the edges. The data showed that the vortex weakens as you go higher. The winds slow, the signature fades. By the time you reach the lower stratosphere, the storm is almost invisible. It is a tropospheric feature, not a stratospheric one. The influence extends upward, but the main body of the storm is confined to the lower atmosphere where water and ammonia condense. The combination of Hubble and JWST wind measurements enabled three-dimensional tracking. Hubble saw deeper clouds moving at 150 meters per second. JWST saw shallower clouds moving at 50 to 70 meters per second. The vertical shear is significant. The storm is not uniform in the vertical direction. It is layered. Each layer moves at a different speed. The fastest winds are near the base. The slowest winds are near the top. The shear is part of what keeps the storm organized. If the winds were uniform, the storm would lose its structure. The aerosol enrichment within the vortex was another JWST discovery. Aerosols tower up to high altitudes inside the Great Red Spot. The cold center forces condensation, but the turbulence lofts the particles upward. The particles are small, micron scale. They scatter light efficiently. The scattering is what makes the storm visible. Without aerosols, the Great Red Spot would be transparent. With aerosols, it is opaque. The aerosol distribution is not uniform. It is thickest near the center, thinner at the edges. The gradient matches the temperature gradient. Cold center, thick clouds, warm edges, thin clouds. The physics is straightforward. The phosphine enrichment is less straightforward. Phosphine is produced deep in the atmosphere. It should be destroyed at the altitudes where it was found, but the upwelling at the periphery of the storm brings it from below. The sinking in the center traps it. The UV light photodissociates it. The products might contribute to the red coloration. The chain of reasoning is plausible but not proven. The red color could also come from tholins, produced by UV irradiation of ammonium hydrosulfide and acetylene, or it could be a mix of both. Or it could be something else entirely. The chemistry is complex. The observations are ambiguous. More work is needed, but the depth is settled. 300 to 500 kilometers. The oscillation is settled. 90 days. The origin is settled. 1831 from wind shear instability. The feeding mechanism is settled. Smaller storms collide and transfer energy. The shrinkage is settled. Minus 0.3 degrees per year in recent decades. The future is less settled. Stabilization is likely. Disappearance is possible. Growth is conceivable. The Great Red Spot is in flux. Not dying, not static. Evolving. 1979. Voyager. One transmits the first detailed image of the Great Red Spot from 9,200,000 kilometers away. Cloud details as small as 160 kilometers across are visible. The colorful wavy cloud pattern to the west of the spot shows extraordinarily complex and variable wave motion. The image is iconic. It defines the Great Red Spot for a generation. But it is just a snapshot, a single moment in a 190-year story. 2017. Juno drops to 8,000 kilometers above the storm. The spacecraft captures images from closer than any mission before. The detail is stunning. Spirals, filaments, turbulence. The storm is not a uniform oval. It is a fractal mess of eddies and swirls. The microwave radiometer penetrates beneath the surface. The gravity instruments measure the mass anomaly. The data revolutionizes understanding. The Great Red Spot is no longer a mystery. It is a data set. 2024. Hubble watches the storm oscillate. JWST maps the chemistry. Ground-based observers track the shrinkage. Numerical models simulate the feeding mechanism. The story comes together. The Great Red Spot formed 190 years ago. It grew. It peaked. It is shrinking. It will stabilize. It will survive. The mechanism is understood. The physics is clear. The future is predictable, within error bars. And here's the kicker. The Great Red Spot is not unique. Jupiter has other long-lived ovals. Oval BA formed in 2000 from the merger of 3 white ovals. It turned red in 2006. It is smaller than the Great Red Spot, but it follows similar dynamics. The northern hemisphere has cyclonic features that persist for decades. The poles have polygonal arrangements of giant cyclones. 8 in the north arranged in an octagonal pattern, 5 in the south arranged in a pentagonal pattern. Those cyclones stay in the same locations year after year. Juno data shows they are extremely resilient. They want to move poleward, but the cyclones at the center push them back. The dynamics are different from the Great Red Spot, but the principle is the same. Organized flow trapped by jet stream sustained by internal heat. Jupiter is not calm, it is violent. The atmosphere churns, the storms collide, the jets accelerate, the vortices spin. But within that violence there is order. The Great Red Spot is proof. 190 years of continuous existence in a chaotic environment. The storm is not an anomaly. It is a consequence. The natural outcome of fluid dynamics on a rapidly rotating gas giant with strong internal heat flux and complex jet stream structure. The Great Red Spot is what happens when the physics is right. And the physics is strange. stranger than we thought. The storm is younger than we believed. It is fed by smaller storms. It is trapped by jet streams. It oscillates on a 90-day cycle. It is cold in the center. It generates heat in the stratosphere. It extends 300 to 500 kilometers deep. It has its own gravity. It breathes. It evolves. It refuses to die because the system sustains it. Every part reinforces every other part. The storm is not fighting Jupiter. It is Jupiter. That is the reason Jupiter's great red spot refuses to die. Not ancient, not immortal, just in balance. The jet streams lock it at 22 degrees south. The smaller storms feed it energy. The cold center organizes the condensation. The depth anchors it against disruption. The internal heat drives the convection that maintains the flow. The oscillation is the storm adjusting to its environment. The shrinkage is the storm finding equilibrium. The survival is the storm being exactly what it needs to be to persist in the only place it can persist. 190 years and counting, the largest known vortex in the solar system, shrinking but stable, oscillating but persistent, strange but understood. The Great Red Spot is not a mystery anymore. It is a solved problem. And the solution is weirder than the myth ever was.